Hi, welcome to Sunil Maths tutorial Fourier series class number 5. In this video we solve a problem where the interval is defined into two parts. Let us see. So expand f of x where f of x defined like this. F of x is equals to 1 over the interval 0 to 2 pi and f of x is equals to 0 over the interval pi to 2 pi, over the interval from pi to 2 pi as Fourier series. It means the function f of x is a discontinuous. The function f of x is discontinuous at the points pi. So here in the interval from 0 to 2 pi, the function behaves like this. From 0 to pi, from 0 to pi, the value of the function is 1. From pi to 2 pi, the value of the function is 0. So by using this, we solve our problem. So in initial stage, given that I write the function f of x is equals to 1 for 0 less than x less than pi and 0 if pi less than x less than 2 pi. Now the Fourier series of f of x in the interval from 0 to 2 pi is given by, this is known formula, f of x is equals to a naught by 2 plus summation n is equals to 0 to 1 to infinity an cos nx plus summation n is equals to 1 to infinity bn sin nx. Now where a naught is equals to integral 0 to pi, integral 0 to 2 pi f of x dx. According to our definition of our function, integral 1 by pi integral 0 to pi f of x dx plus integral pi to 2 pi integral pi to 2 pi f of x dx. According to the given interval, we divide the integration limits from 0 to pi and pi to 2 pi. You see there, if x less than 0 to pi, the value of the function is 1. If x lies between pi and 2 pi, the value of f of x is 0. So here the integral takes the form 1 by pi integral 0 to pi. From integral 0 to pi, the value of the function is 1 dx plus integral 2 to pi, I'm very sorry, integral pi to 2 pi, integral pi to 2 pi, integral pi to 2 pi, between pi to 2 pi f of x value is 0 dx. So see, the second integral completely vanishes, this becomes 0. Again the second interval gives a value of 1 by pi integral dx x limits 0 to pi. You simply get 1 by pi into pi and finally you get 1. Therefore a naught is equals to 1. A naught is equals to 1. So this is the important part here. We divide the integration from 0 to pi 2 pi as two parts. Integral 0 to pi plus integral pi to 2 pi according to our function. Now an is equals to 1 by pi, 1 by pi. Here also same, integral 0 to pi f of x cos nx dx plus integral pi to 2 pi f of x cos nx dx, cos nx dx. Again here also integral 0 to pi, the value of f of x is 1. Integral pi to 2 pi, the value of f of x is 0. So this second integral completely becomes, this integral completely becomes 0. So we solve only first integral 1 by pi integral 0 to pi, the value of f of x is 1. So you simply get just cos nx dx. So again it is equals to 1 by pi integral cos nx 1 by n sin nx, 1 by n sin nx, and the limits are from 0 to pi. So you can write 1 by n pi cos n pi, I'm substituting the limits, sin n pi minus sin 0 degrees. So we know that a simple values sin n pi is equals to 0 for all n belongs to z, and sine 0 is also equivalent to 0. So it means the value here 0, it is also 0. So finally 1 by n pi into 0, 1 by n pi into 0, you get 0. This condition shows us an is equals to 0. An is equals to 0. Already we find that a naught is equals to 1. Now it is an is equals to 0. Now we go for bn. Here also you can write like this: 1 by pi, 1 by pi, integral 0 to pi f of x sine nx dx plus integral pi to 2 pi, integral pi to 2 pi f of x sine nx dx. So again same, here in the interval from 0 to pi, here in the interval 0 to 2 pi, the value of f of x is 1. F of x is equals to 1. Here the value of f of x is 0. So obviously this second integral is completely 0. So we get this 1 by pi integral 0 to pi sine nx dx. Integral sine nx minus 1 by n cos nx. 1 by pi minus 1 by n cos nx, limits 0 to pi. So you simply get minus 1 by n pi, upper limit cos n pi, minus lower limit cos 0 degrees. We know that cos n pi is equals to minus 1 power n, cos 0 degrees is equals to 1. So applying that, minus 1 by n pi minus 1 power n minus 1 minus 1. So from this, here we get two different values. Here we get two different values for our bn. So we check this: minus 1 by n pi minus 1 by n pi 1 minus 1. This condition happens if n is even. If n is even. Minus 1 by n pi minus 1 minus 1 if n is odd. If n is odd. So whenever n is even number, bn is 0. Whenever n is odd number, something you get. So this term is 0 if n is even, and the second term is minus 2 minus of minus plus, again minus of minus plus. You get simply 2 by n pi if n is odd. If n is odd. So using all these values of a naught, using a naught, an, bn, in Fourier series expansion, we get f of x is equals to 1 by 2 plus 2 by pi summation over n is equals to 1 comma 3 comma 5 comma and so on up to infinity. Only you are using odd numbers. 1 by n sine nx. 1 by n sine nx. In another words, 1 by 2 plus 2 by pi into sin x plus 1 by 3 sin 3x plus 1 by 5 sin 5x plus and so on. This is the required Fourier series for our given problem. So these types of problems are known as functions, Fourier series for the functions with discontinuities. With the discontinuities, you observe that here our function f of x is equals to 1 and f of x is equals to 0 is also discontinuous at pi. It behaves differently. From 0 to pi it is 1 and from pi to 2 pi it is 0. So in this type of problems you have to split the integration. Here because of integral everywhere you have to write integral 0 to 2 pi, but that integral can be split into 0 to pi plus integral pi to 2 pi. That is the important part here. After splitting, you can use the different values of the function f of x. So practice the problem, and I give one similar problem to work out. Write down. Suppose f of x is equals to minus k if minus pi less than x less than 0 plus k if 0 less than x less than pi. Then find Fourier series for f of x. Then find Fourier series for f of x where k is a constant. Where k is a constant. So applying the this splitting integration, solve this problem. In the next video we solve one more problem. Keep learning.